Howdy everyone. This is part 2 of the partial differential equations examples. Now I'm going to do the heat equation. It's very similar to the wave equation, but it obviously has some distinct differences that we have to pay attention to. However, this one is actually quite shorter than the wave equation because you have less boundary conditions that you have to work with to refine the equation. Alright, so let's get into it. One end A of an insulated metal bar AB of length 2 meters is kept at 0 degrees while the other end B is maintained at 50 degrees Celsius until a steady state temperature along the bar is achieved. At T equals 0, the end B is suddenly reduced to 0 degrees and kept at that temperature. Using the heat conduction equation, determine an expression for the temperature at any point in the bar distance x from A at any time t. Okay, so with this one here, we have an initial condition where the heat at A is 0 and at B, which is 2 meters away, is equal to 50, right? Then once B is quenched, you have some function that would look like this, right? Where the heat is 0 at A and it's 0 at B. Yeah, so we now need to identify what all the boundary conditions associated with these two descriptions of our system are. And the very first one that we have here is that we have this linear function that that occurs at when time is equal to 0, right? And we know from the last video that this linear function can be represented by using the standard linear equation, y equals mx plus c. So if we call this function f of x, which is equal to y, which is equal to m of x plus c, right? We first would have to find the gradient of this function, which is y2 minus y1 over x2 minus x1. Okay, then y2 is 50, y1 is 0, x2 is 2, x1 is 0. That's going to give us 25. Then we've got y is equal to 25x plus c. Now we need to find c. So we'll just evaluate it at any point along this linear function. I'll literally just use this starting point here where both y and x are equal to 0, which would mean that c is equal to 0. Therefore, our function f of x, which describes the initial condition of the heat along our bar, is equal to 25x. Sweet. So the next boundary condition will be of when t is no longer 0, right? So for the point, but when x is 0 and t is no longer 0, then you've got this being equal to 0. And when x is at the other limiting point here, the other endpoint, at any time t is going to be 0. Right? So now let's describe a general solution for our system. We know that we can we can assume a general solution of a function in terms of x times a function in terms of t that will give us our general solution. The equation for heat is d of 2 of u over d of x squared uh, equals to 1 over c squared d of u of dt. So the only difference between the heat equation and the wave equation is that the partial differential with regard to t is a first order differential instead of a second. Okay, so now we can represent this using this symbology, but first we just need to differentiate that. So get the partial differential in terms of x. That is equal to x prime of t, then the partial differential with respect to t is equal to x. Nasty. X t prime. Lacquer. Now we get the second partial derivative with regard to x. That's going to give us x double prime of t. Okay, so now that means our equation here can be represented as x double prime t, which is equal to 1 over c squared x t prime. Now we're going to assume that c squared is equal to 1 unless they specifically stipulate what c is. It's best to just assume it to be 1. Okay, so that's going to be x double prime t equals to x t prime. Then we can rewrite that as x double prime by getting all of the like terms on one side, t prime over t. Now we know that these two ratios are equal to a constant that we represent as minus p squared. So isolating both sides, excuse me, is equal to minus p squared. Sorry, yeah, it's tough out here. Minus p squared. Let's just blow my nose. Okay, so both of these can then be rearranged to be p squared x is equal to 0, t plus p squared is equal to 0. Okay, and the general solution for that is, as we know, a cosine p of x plus b sine p of x. And then for t, it's going to be some constant c multiplied by e to the negative p squared t. And so u of x of t is now given our first general solution, a cosine px plus b sine p of x multiplied by c e to the minus p squared t. Dope. Okay, so